Anyway, it's a lovely Tuesday morning. Sun is shining, which is why I'm sort of a bit dark here. We're going to be talking about the uses of haloalkanes, what they're used for, what they were used for, and the problem that's caused to our environment, and some more bits and pieces like that. So let's get on and do that. So we're going to be talking about organohalogen compounds in the environment. So we're going to look at some of the uses, and we're going to look at the big environmental disaster that happened around the 80s and 90s with regards to the ozone layer and the poison that we'd given it because we used some compounds irresponsibly. They were thought to be really good compounds, but actually it wasn't so good. And we're going to be talking about some equations, etc., about how the Earth's protective ozone atmosphere looks after itself. So, firstly, we have to understand what ozone is. And ozone is a fantastic state of oxygen. It is O3. It's not a particularly stable state, but that's quite advantageous. Oops, I've just gone straight past the bit. Let's go back. It's a really, really important state of oxygen. It has oxygen in 3 atoms as the molecule. As you can see, it's got this sort of like plus charge, which is sort of delocalized around. Delocalized just means it sort of moves around. So even though the plus charge and the little minus charges are here, this is all over the molecule. It can be really good because up in the upper atmosphere, actually it really helps us because it shields us from ultraviolet light, which can give us skin cancer, etc., and sunburn. So it's a really, really good thing. I've got a little bit of a cold, by the way, I do apologise. But it can also be a bad thing because if this is created lower down in the troposphere, actually it can cause damage to health, can cause asthma attacks. It's not very nice. It's quite an irritant of a gas, which is if you have a machine that actually makes ozone, like for example lots of laser printers and things make ozone, they have to have ozone filters in them now just because it's not a very, very nice gas because it's really, really reactive. So let's talk about these ideas of troposphere and stratosphere. So a little bit of geography. Hopefully the geography teachers won't see me doing their geography because they'll probably get very upset if they see me doing this and getting it wrong. So, oh, look at this animation. We have the lower part of the atmosphere is called the troposphere. We live in the troposphere. Above the troposphere, and we're talking at least sort of 15, 20 miles up, we have the stratosphere. And the stratosphere is the next layer of the atmosphere. And that part of the stratosphere has the ozone layer in it. On top of the stratosphere, we have the mesosphere. And this extends right out into space, really, really far away. But we can see from the animation that Earth is constantly being bombarded. I'll see if I can get the no, I can't get that going again. Earth is constantly being bombarded by ultraviolet radiation. And what the ozone layer does is it filters out some of the radiation. And we want to know how it does that. And if we look at a profile of the radiation that's hitting the Earth, so this would be UVA, which is our long wavelength radiation, so we're talking 320 nanometers to 400 nanometers, so we're talking sort of nearly to the visible spectrum. We can see actually quite a lot of that comes through. UVB, which is 288 nanometers to 320 nanometers, most of that is filtered out by this layer, which is at around sort of 20 kilometers high, and this would be our ozone layer. The really, really nasty stuff, the UVC, that is totally filtered out by the ozone layer. So the big thing is, if there's no ozone layer, we have a big, big problem. So we'll talk about UVA, B or C. Which one has the highest energy? Now we have to remember when we're talking about wavelength, wavelength is literally how long a wave is. If it has a shorter wavelength, it has a higher energy. It's the inverse to frequency. So shorter wavelength, higher energy. So if we look at UVA, 320 to 400 nanometers, as I said, 400 nanometers is just out of the violet, so it's sort of considered ultraviolet, but it's sometimes visible. UVB definitely invisible, UVC definitely invisible. But each of the photons or the packets of light that sort of hits you, if you have a UVA packet of light hit you, it's going to have quite a reasonable amount of energy. UVB is going to have more energy, UVC is going to have even more energy. And if you think about it, if those packets of light are hitting your DNA, UVA is going to have least chance of damaging your DNA. UVB is going to have more chance. UVC is going to rearrange that DNA and give you skin cancer. So really, really bad news. We don't want this getting down to our where we are in the troposphere. So, how's the ozone layer work? Well, firstly, what happens is ozone, being O3, can dissociate and become O2 and oxygen, and what it needs is a photon of light to do that. So what happens is, and I'm going to try drawing one on there. Good luck to me, because you know how. Oh, that didn't work at all, did it? Let's give it another go. So if we have a photon of light hitting our ozone, what will happen is it will split up and become O2 and O. Now, this is really, really important, because what happens is, as soon as this change occurs, it filters out that photon of light. So if we have lots and lots of ozone in the upper atmosphere, it will filter out the UV light by changing O3 to O2 and O. Now, what can then happen is the O2 and O can come back together, forming ozone again. So it sort of keeps itself going. So this is the reverse reaction happening, and it gives off a little heat in doing that. The heat's not really that important, but what we can see is it's a reversible process. And we can see that because the radiation is being absorbed by the ozone molecule and breaking it up, it's effectively taking out that radiation from the atmosphere. And this is really helpful to us, because if we're on the ground and we're sort of out on the beach tanning ourselves, obviously putting on the correct factor of sun lotion, it means the really, really, really harmful radiation from the sun is being filtered out, or most of it is, if everything's working correctly. But it stopped working for a while, and I'll talk about why it stopped working later. So, back in, I think it was about the 60s, there was a scientist who created these things called CFCs. And a CFC is a chlorofluorocarbon. And looking at the structure of these things, see if I can draw one on here. Again, this could go horribly wrong. So we've got C, and we'll just put another C next to it. I'm getting better with the use of this. Oh dear. Here we go. We've got C. We'll put a couple of F's in there. Cl, Cl. Do a bit of F there. So we have a fluorochlorocarbon. There are no hydrogens in here. This isn't a hydrocarbon. This is just a fluorochlorocarbon. And if you think about it, we discussed yesterday, the chlorine-fluorine bonds are very, very strong. The carbon-fluorine bonds are very strong. The carbon-chlorine bonds are comparatively very weak. So if this gets exposed to some light, if it gets up into the upper atmosphere, what will happen is this bond here, the bond here, will start breaking, and that will undergo some homolytic fission, making a chlorine radical. Now, chlorine radicals are not nice, and I'll show you why they're not nice later. But this chlorine radical can break down ozone, and it can do so catalytically. So, CFCs we use quite widely, and they were used for everything. They were seen as a miracle compound, especially with refrigerators. What they used to put in refrigerators was ammonia, and anyone who's ever been exposed to any ammonia, or anyone who I've sort of said, yeah, you have a sniff of this, and you go, oh gosh, that's ammonia, they will know it's not a very nice gas. And what they used to do is they used to fill refrigerators with ammonia, because ammonia has a quite convenient boiling point, which means it's good for refrigerating things. They filled the elements of fridges with ammonia, and then because ammonia is such a nasty gas, they would start corroding and things like that. It'd take a few years and suddenly there'd be a big leak of ammonia, so it wasn't very nice. They also used CFCs in solvents, cleaners, propellants and aerosols. Forgot to say, actually the reason why they changed to CFCs is because instead of this nasty, horrible, corrosive gas being used, they could use CFCs which were non-toxic. In fact, when they actually sort of bought these gases out, the inventor quite proudly went into a trade show and breathed in a lungful of CFCs to show how non-toxic and inert his gases were. How wrong they were. Not toxic to him, but it was very toxic to the planet. So they've got all these CFCs, compounds that just contain carbon, fluorine and chlorine, and they started using them widely. And these things started to eventually start propagating up to the atmosphere. It caused this massive trouble of a hole in the ozone layer, and I'll show you why pretty soon. But they were then banned, and the Montreal Protocol was signed, which banned their use, replacing them with hydrofluorocarbons, which are nowhere near as bad, but they're also really big greenhouse gases, but that's another thing. So, Frank Sherwood-Rowland and Mario Molina, they won the Nobel Prize for discovering that CFCs were breaking down in the stratosphere. And it's quite interesting. Have a quick read of these links. You can get them on the PowerPoint, or just put Nobel Prize 1995 and you will see them. It is really interesting to read the story, because actually they ignored the data on this for quite a while because they thought it was a mistake. So it's quite an interesting story to read, but it's well beyond the scope of what we're talking about today. So if we have a look at this animation, hopefully it'll work. Give me a moment. Put it back onto pointer. That's not working. There we are. I can run this anyway. We can see that the hole in the ozone layer, which is what this represents, is getting, it's quite stable, but it's starting to shrink as we're getting closer to 2014. And the reason for that is because we stopped using CFCs. This hole here is where there is a shortage of ozone, and we can see actually going to Antarctica, which is what this represents, is going to be very, very bad for your health, especially if you don't wear proper sunscreen. But we can see actually, as we're getting towards the end of December, that the hole is closing up. So it's a seasonal hole rather than something that happens all year round. So what happened was they started measuring ozone layers, or they measured the amount of ozone, and they noticed that it started going downwards. But they didn't notice it for quite a while. They thought it was actually just a proper error that was going on. But actually this was a real thing. And they found that instances of skin cancer, were going up in the southern hemisphere. And the reason for this was because there was no ozone protecting them. So what's the problem? Well, actually, if we have something like ozone breaking down to make oxygen and normal oxygen O2, usually that then goes backwards and creates more O3. However, if we start breaking up CFCs, we end up getting a chlorine radical, and that's your chlorine radical there. What kind of step is it? We're going from a non-radical species to two radical species. What step would that be? What I'm hoping you say is initiation. We're going from no radicals to radicals, so therefore it's initiation. It is starting the radical reaction. So, what breaks the CFCs down? The thing that actually happens is we have ultraviolet light which shines on one of these, it breaks the weakest bond, and the weakest bond happens to be the carbon-chlorine bond. So what happens is we make chloride radicals, Cl radicals. So if we have chlorine radicals, what will happen is that will react with the ozone, and it will make a chloroxide radical and some oxygen. You do need to know these equations, so please make sure you keep an eye on them. Maybe think about writing them down. Excuse me. Chlorine radicals then break down they react with more oxygen, making oxygen gas and regenerating the chlorine radicals. So what we've done is we've destroyed an ozone molecule. We've made an O2 molecule and a chloroxide radical. The chloroxide radical has reacted with an oxygen radical and just made oxygen. So we've not regenerated this ozone. But what we have done is regenerated the chlorine. So if we have a reaction, we put something into it which is there at the end of the reaction and causes a reaction to happen, maybe by lowering the activation energy or changing the pathway of the reaction. What's that called? What is that chlorine? What can it be regarded as? What I'm hoping you're saying is the chlorine can be regarded as a catalyst. So if we look at the two propagation steps and add them together, so what we do is we just put them together and we take away anything that's on both sides of the equation, we can see we have O3 plus O becomes two O2s. And because chlorine is on both sides of the equation, chlorine is a catalyst. It's a homogeneous catalyst. We've not really spoken about homogeneous catalysts, but we have spoken about catalysts. A homogeneous catalyst is a catalyst which is in the same state of matter. So they are both gases, gaseous. So a homogeneous catalyst is something that's in the same state of matter. Now, if we think about it, the most of the catalysts that we come across in chemistry, like manganese dioxide in hydrogen peroxide, they are heterogeneous catalysts. So this is a really good example of a homogeneous catalyst. So the big thing is that each chlorine radical can destroy about 50,000 ozone molecules. It says thousands, I'm pretty sure the answer is about 50,000. So this means that a tiny little bit of a CFC getting into the atmosphere can cause a massive piece of damage to the atmosphere. This isn't just chlorine radicals that can do this. We also are causing damage to the ozone layer by things that we're doing all the time. So NO, nitrogen oxide, is made by aircraft engines. It's made by the combustion process when our 78% nitrogen atmosphere goes into the combustion chamber of an aircraft, so into the jet engine. Naturally, some oxygen will bind with that and it will make nitrogen or NO radicals. The NO radical can also react with O3 and it can make NO2 radicals and oxygen, so again destroying ozone. And if we look again, we have this breakdown. So this is a problem. We can see the NO is also catalytic. But the only way we would be able to stop that is to not fly aircraft at the moment with the current technology we have. So unlike the CFCs, where actually they could just get rid of the CFCs, they can't do this currently with aircraft. So that's about it really. As I said, you have to make sure you understand that we have some uses for CFCs, or sorry, haloalkanes. They're not all good uses. They have caused problems to the atmosphere before. They are still causing problems. But I think it's a really, really important thing to remember. Actually, not all things that we do in chemistry are good. So, here's your tasks for today. Feel free to pause this, or if you have a look at the comments section, I will also paste it into the comments section. Thank you very much for listening, and I hope you have a good day.